All right, so next up we have Elizabeth Bennewitz from the University of Maryland College Park. Her field is physics, and her advisor is Alexei Gorshkov, and the practicum is at Lawrence Berkeley National Laboratory. So, go ahead.
Great,
Thanks.
Thank you so much. Today I'm going to be talking about quantum simulation with analog quantum processors, and in particular focusing on the role of high-performance computing in being able to develop experimental protocols to study physics in new ways using these analog processors, but also to be able to develop highly precise models of the dynamics that are occurring on these processors themselves. So to begin, the goal is very generally and very broadly to simulate strongly interacting quantum many-body systems. And typically, we have two types of tools at our disposal. The first is some sort of classical simulation of these models. And this is typically limited to smaller systems, low entanglement, or you have to make certain types of approximations on the systems that you're trying to study. And sometimes this is good enough for the problems that you want to look into, but sometimes it's not. And we really want to push the types of physics that the types of systems that we can look at. And that's why we've recently been developing all of these quantum tools. And these quantum tools fall into one of two categories. The first one is something called digital quantum simulation. This is your conventional quantum computation, where you take your problem and you discretize your problem onto discrete logical gates that form a universal set for computation. And this is really just doing like some sort of using a quantum computer to solve the system that you're interested in studying. The other thing you can do is you can use analog quantum simulation, where you have some sort of engineered Hamiltonian on your device. And this could actually be exactly the same device that you're using to do quantum computers, but you're turning it into an analog mode, where now you have access to kind of one gate, which is a continuous time evolution of some sort of engineered Hamiltonian. And these simulators are really promising and really exciting, especially right now, because they offer a path towards studying interesting and also classically hard and challenging problems. And that's due in part to the ability to directly implement the Hamiltonian dynamics that you want to study, so you don't have to discretize this problem, which can give you errors or make you subject to noise. And also you have fast evolution and fast entanglement growth. So depending on the problem that you're studying, you could get into this regime where entanglement grows very quickly and quickly get into this strongly interacting regime, which is very difficult for classical computers to model. So in particular, what I want to focus on in this talk will be two parts. One is how we can use high-performance computing to develop better processors, and this we're doing via learning the device physics via Hamiltonian learning. And then the other one is to design experiments. So once you have these analog processors, how can we use them to figure out how to probe physics in new ways? So diving into the first one, which is precision modeling of analog quantum processors using high-performance computing. So the problem that we're sitting in is you have some sort of analog processor. In this case, for this project, we focused on superconducting analog processors, where we have a 2D grid of coupled transmons. And inside this, you have this is a fabricated circuit, and you have these circuit elements which represent your qubit, and you engineer some sort of qubit-qubit interaction. And now what we do is we turn all of these on, so we allow all of these qubits to interact with each other, and we obtain an effective spin Hamiltonian. So this Hamiltonian describes all of the dynamics of interest on your device, and we ask the question, okay, how well do we know each one of these parameters? And you can kind of start with your best guess for what this Hamiltonian is based on kind of 2-qubit spectroscopy or kind of underlying engineering of the device. But when you turn everything on, how accurately do we actually know this Hamiltonian itself? And can we make any improvements? And that's where we use this proxy called XEB fidelity. So we can verify the dynamics or kind of check to see how well we understand the Hamiltonian by comparing the experimental data to classical simulation. So we'll take a bunch of measurements on the experiment, and then we'll do some sort of classical simulation. So we'll do real-time evolution of what our best guess for the model is, and then we compare it with this XEB fidelity. And for those that are interested or those who are in the field, this is actually the same metric as the one used in the quantum supremacy experiment on random unitary circuits. But it also works as a fidelity estimator in the context of these analog platforms. And so any sort of modeling errors, so we compare the experimental data, and if you have any sort of difference between what you expect to be happening and what is actually happening, this will cause this XEB fidelity to decay. And we can also set an upper limit on this, which is set by noise. And this gap is actually completely kind of created by any sort of modeling error. So clearly there's a lot of room for improvement in what we can actually extract and harness. If we fine-tune all of these Hamiltonian parameters, we have a lot to gain. And so it kind of begs the question, can we actually reduce these modeling errors by what's called Hamiltonian learning, or really, how do you get these microscopic parameters of your Hamiltonian? So the way that we do this is we turn it into an optimization problem, which everyone in this room is very familiar with, like just the concept of optimization. And so here what we do is we start with some sort of device model. So this could be any sort of knowledge that you have about your device. We perform this classical simulation to get this XEB fidelity. And then we fine-tune all of these Hamiltonian parameters to get higher and higher XEB scores, which tell you that you have your model is more and more faithful to what is actually happening on the device. And so we learn these microscopic parameters of the device by optimizing XEB fidelity. And what's really great about this is it makes use of the existing knowledge on the device. So we're not starting from scratch. We know a lot about the device. You can do a lot of highly precise calibration, but we want to take things one step further. And it also has very simple experimental control. So we can do this on experimental data. So if we have kind of 4x4 subgrids on a chip, we have some initial XEB decay curve coming from kind of existing knowledge on the device. And then we can optimize this XEB fidelity at a particular training time. And what we see is that we're able to get higher and higher XEB curves by fitting this Hamiltonian via this optimizer. So here we actually get a 4 times improvement in XEB decay after fitting all of these 300 parameters. But that's great, so we're kind of learning on all of these individual patches, but 16 qubits isn't that much, and we ideally want to figure out how to do this kind of at a larger scale. And so how do you scale this to larger systems? And the way that we attempt to do this, although this, is that we stitch together results learned on these patches. So let's say you want to learn the Hamiltonian on a 5x5 grid. What we'll do is we'll learn on these smaller patches, and then we'll stitch them together by saying, oh, if we have some coefficient on some term I, and if it has the same neighborhood as the rest of the patch, then we will average all of the results together. And this takes advantage of the ability to tune interactions on and off. So for example, in these superconducting platforms, you can actually turn off these qubits, so they're actually not interacting with everything in this blue square. And then we just learn kind of the physics and the dynamics happening here. And because the physics on the device is fairly local, this is a good approximation up to some neighborhood matching of what's happening on this larger grid. And there's actually a sweet spot. So you don't want these patches to be too small, because if they're too small, then you're not capturing all of the interactions that could be occurring on your device. But if they're too large, then the classical compute becomes overwhelming, and you aren't able to compute these gradients and optimize the problem. So you have to sit in this sweet spot where your patches are big enough to capture the local interactions on the device, but they're also not too big where optimizing becomes a bottleneck. And so we can do this to stitch together to a 5x5 patch. And this is a kind of an earlier kind of proof of principle where you learn on these individual patches. You have an initial decay rate. And then we see that we're able to improve this XEB decay rate on this larger patch that we didn't directly train on. And so this is a really nice way to kind of scale it up. And we're currently working on kind of scaling this to even larger systems and validating it as well. But really kind of want to highlight that we're using this classical post-processing, which is we've kind of packaged into this Hamiltonian learning framework to obtain this ultra-precise modeling of the underlying Hamiltonian dynamics on your analog processor. And so now that we have a fairly good understanding, or one example of how you can use high-performance computing to improve your underlying device and knowledge of the device, let's now kind of briefly go through some examples of how you could use these devices to study physics in new ways. So in particular, there's many different kind of application areas of using quantum simulators and quantum computers. One of these areas is in high energy and nuclear physics. And one such example is studying confinement. So confinement is a feature of the strong force. And so the strong force confines quarks and gluons into bound states of mesons and baryons. And if you were to try to pull apart quarks, it takes an infinite amount of energy to separate them, which is actually why you never find them on their own. And what happens is when you pull them far enough apart, this string that's kind of has some string tension in between them will actually break, and you'll create a new quark and antiquark, so you have two new bound states. And this is called confinement. And it's kind of, there's this feature of kind of this exponential potential between two quarks as you pull them apart. And so as a proof of principle to thinking about how we can study kind of characteristics of the strong force on quantum simulators, can we study toy models of string breaking and scattering of confined particles in analog processors? So there's an analogous form of confinement, and I kind of want to emphasize this analogy, where we kind of have one story on one side and another story on the other, and there's this commonality between them, which is that confinement has also been shown for the Ising model, where kinks are confined. So kinks here are kind of anti-aligned regions of your spin chain, and if you have two kinks, kind of 1 and 2, these are going to be analogous to our two quarks that form bound states of mesons. And if you pull these kinks apart, it takes an infinite amount of energy to separate them. So you get this similar kind of asymptotically infinite curve. And so you have this analogy between confinement that shows up in the strong force and confinement in spin chains. And so this makes analog simulators a simpler testing ground for trying to figure out how you could ask these questions. How can we study string breaking, or how can we study scattering kind of within this quantum simulation framework with these new tools? Oh, yeah, okay. So the first one we can think about is studying string breaking. In contrast to maybe ways that this is done classically, where you study static properties of QCD, analog processors are really good at getting real-time evolution, so performing time evolution under this Hamiltonian. And so we'll focus on this idea of dynamical string breaking. And so here you start with some string where it has no tension, and then we're going to quench it to a string that has tension, and we want to see how this string breaks as a function of time. And so this can be done in a real experiment. So you start on the bottom here with this string that has no tension, and then you quench to a string that does, and then you see that this chain is oscillating between a broken and an unbroken string. And in particular, as you increase string tension, it's breaking near the edges and then propagating inwards, especially when you go to higher string tensions. And so here in this framework, in the way that we studied this, the string breaks at the edges and then propagates into the bulk, which is different than the conventional Schwinger mechanism, which predicts charge pair formation, initiating in the bulk and then propagating to the edges. But this is just kind of one such example of how you could start to look at the dynamical processes that occur in these strongly interacting settings used in analog processors. The other thing we could look at is scattering. And so in general, for a scattering process, you want to have 3 steps. The first one is you want to prepare wave packets. So you prepare wave packets of these kind of single spin flips, and you want them localized in some place so that you can also give them momentum so that they can scatter towards each other. So we developed an experimental protocol for preparing wave packets using the intrinsic interactions on an analog device, and in particular in a trapped ion analog device, where we perform a quantum bus-mediated protocol where we start with an excitation in a vibrational mode, and we transfer it into this spin excitation, and then we do the second one to transfer it into the second wave packet. Once you prepare wave packets, you can collide these particles. So then you turn them on, you allow them to interact. They interact and scatter with each other, and then they form outgoing states. And so scattering is useful as a process in general because you can kind of very probe kind of all these strong interactions in particles by looking and seeing what they create. And this step is just real-time evolution under a Hamiltonian. And then you can also measure outgoing states. So you have to figure out how to do some sort of metrology on your system to figure out what is coming out of your system. And so here we also thought about how you could diagnose what's happening at the end of this protocol. But really this was a kind of a proof of principle where we developed protocols in order to test this out in a scattering protocol, or on an analog processor. And so to conclude, these analog processors are really promising paths towards studying interesting and hard problems. And high-performance computing, we can think about these analog processors both as a type of high-performance computing where we're getting access to something that would be very hard to get classically. But we can also use kind of conventional notion of kind of classical supercomputing to validate experiments and obtain ultra-precise modeling, but also to design these experiments and probe physics in new ways. And so thank you, and thank you especially to the CSGF. Thank you. All right.